Mr. Frost, are you there?
Hello. Yes, we've got the whole team. If my video pops up, not the whole team, so just four of us.
That team was from Poland, so you're from Western. We're going from literally around the world in just an instant. So
yeah, I guess so.
these are modern times we're in.
Sorry, let me just get this sorted out real quick. There we go.
It's 3 in there, huh?
Yeah, a little bit. A little early hours, but we've made the trek down to university, so we'll be here.
Wow.
Yeah.
All right. Well, let's see. Your rocket has an air brake system. Did I get mixed up, or is that okay?
Yeah.
Could you talk a little bit about that design, what trade-offs you made, and maybe any challenges you had while implementing that design?
Sure. So Airbrake's design still not 100% finished, but as of this stage, we've opted for a disc brake system where the flaps go perpendicular to the airflow, as opposed to hinge system where they come up like that. And one of the main reasons was space. And so because our motor tube is 100 mil and the rocket is 160, there's only about 30 mil either side at the bottom of the section, at the bottom of the rocket to fit an air brake mechanism. And combined with like the strength it would have to actuate while the rocket is going at full speed, there really wasn't enough space to work with. So we had to, although like a hinge mechanism would have probably produced more drag based on some of the simulations been doing, had to kind of compromise on the disc system. Yeah, I mean that's one of the things I would say.
So when you calculate the or when you how do you decide how much to deploy the air brakes in flight?
Sure. So we have a simulation done with a drag coefficient that corresponds to the air brakes kind of half actuated, I suppose. This is like a middle drag coefficient. And then we change the mass in our simulation until that goes to exactly 10,000 feet. And so that's our reference simulation, so to speak, or the perfect thing that we're aiming for. And then during the flight, so we have a few waypoints as well during the flight. And so at each waypoint, the flight computer will check the velocity and the altitude, and then compare that to the simulation that's the ideal one. And so if the velocity at that altitude is too much, it'll increase the air brakes a certain amount, or if it's too little, it'll decrease. And one of the good things is that it's able to speed up or slow down relative to the simulation. So we're not just once we go over, so to speak, we can actually come back because the simulation's taken at a middle drag coefficient, if that makes sense.
Yeah, that's a very it's a great part of the design is shooting for the right altitude with your air brakes half deployed.
Yeah, exactly.
Rick or Logan, you want to have another question?
Well, I have some more related to the air brake system. Is there a particular control algorithm that you're using to implement this conceptual design you're talking about?
We're still finalizing the algorithm. As far as Toby,
yeah, in the past we had actually run some experiments with a sort of a PID like system that had a little bit of extra stuff going on in there that was looking at the various sensors to calculate the speed and the azimuth and just to try and essentially, actuate the system so that by the time it gets to the peak, that it's at the full actuation. But as time's gone on, we've decided to go with this sort of simulate everything with this half actuated approach. And so as we go forward, we'll probably implement that into the program that controls the actuation of the air brakes as well. Yeah.
Okay. I also noticed you have excellent tables of system requirements at the beginning of every section. That is highly differentiating and was very good. In the Airbrake section.
Yeah, that's something we thought was really critical to, the design report, because everything that we've done is based around those requirements, and it's literally dictated all the decisions we made. So we thought that was quite important, to be honest.
Yeah.
Yes, the competition rewards design documentation much more directly than sophistication. I noticed in the Airbrake section, there's a stability requirement, which is indeed a requirement. The rocket needs to be stable, but I'm unclear on how stability under different drag configurations has been measured, calculated, simulated. Where do you stand with understanding stability under different Airbrake configurations?
Sure. So we've done CFD simulations at different airspeeds and different airbrake actuation extents. And from that, we're able to tell, obviously, the drag coefficient, which is one, but also center of pressure position. And so you can calculate the stability from that, and obviously a lot more accurate than the rocket simulation softwares.
Sure. So I imagine that produces a pretty complex surface of stability margins against different velocities and brake configurations. How do you go about converting this large multivariate data set into a specific, yes/no answer?
Sure. It's actually quite discrete, because we don't, obviously the simulations themselves take hours, and so we're not able to do every single possible continuous range, obviously. So we only do the air brakes at 5 different increments, and the velocities as well, just not that many. So it's quite a small amount of data points, and we're just able to look at it kind of, manually.
And that's something that we plan to sort of implement into the algorithm. So, so part of the work Saichi's been doing is basically we'll develop some kind of profile which will basically relate the amount of actuation you need for a given, speed of the rocket and its current height or whatever. And then we can kind of interpolate between that and work with a bit of the real-time data and have the PID all mixed in together to help it make sure that it gets to the target altitude just right.
Let me jump in and ask a quick question. I saw you made your own parachute, which is very impressive. How did you guys go about testing the seams for opening shock? Do you have any feel for? I don't know if there's a lot of work out in the public domain about how the how a parachute reacts. Do you guys how do you take that make your seams so they wouldn't rip when you open them?
So yeah, for our seams, part of it was informed based on previous designs we've done. So we made parachutes before that have been reliable, that have worked well, and basically that's kind of the same design process was followed for the parachutes we used for this one. Also, it was inspired by the design of parachutes that we bought. So we purchased some parachutes for another project that we did, and we really liked them, and we loved the design, and so we kind of adapted that, and we checked what seams they used. And we did quite a good amount of research on seams and strength and stuff, and with a felt seam for the big parachute. So yeah, just combination of research and past experience on that.
Interesting. Interesting. Did you guys actually use a sewing machine on it?
Yeah.
You do all the work? You
Yeah.
did, huh? Very nice.
Yeah.
Very nice. That's one
Very
thing I've
experiment.
always bought parachutes, but yeah, that's impressive. That shows you, you know, and you saved a lot of money too. Those parachutes are very expensive.
Yeah, oh, exactly. I think it's almost stays true to our roots, because obviously when we started off 3 years ago, we had no funding from the university whatsoever, and it was all out of our members' pockets. So as cheap as we could make it, that was kind of the goal with our first competition rocket. And yeah, and it's just a better experience, I think, getting in as fundamental as you can. You learn a lot more.
Yeah, as a team, it's something we're pretty passionate about. Is you know, this is one of the few times in your life as an engineer, you know, you might go out and work for companies, but often the most cheap thing to do will just be to buy some, you know, most economically sensible decision for the company would just be to buy some pre-existing off-the-shelf system. But you know, this time in our lives at university, it's like when you really can go the extra mile and learn how to make things yourself in a, you know, in a high quality fashion. And that's something that all the technical leads here are pretty keen on perpetuating within the club's culture.
Yeah, and I think it stands beyond parachutes. Obviously, you've seen it in our electronics as well, and all of our airframe as well is completely hand laid. Whereas I know a lot of team will buy their motor tube or buy the body tubes. But yeah, we're passionate about making it.
So you guys also wind your own body tubes, don't you?
Yeah, exactly.
Now, did you build the winder, or is that a commercial winder?
Oh, so yeah, it's not filament wound. It's just hand laid fabric around the mantle, the old-fashioned way. Unfortunately, we don't have access to those luxuries yet. So maybe in the future. Yeah.
Very good.
Our mothers made the winders.
One thing you mentioned in your video was wanting to make a modular design to allow you to do future upgrades. Could you talk about some of the future upgrades that you would like to do?
Yeah, sure. Okay, so one thing definitely would be putting other payloads in. So right now we have just a standard boilerplate payload with the CubeSats, and we've really tried to make that fixture for it really easily removable and adjustable, so that if maybe potentially in the future someone else at the university, maybe in another department, wants to put a payload in, it's very, very easy for them, because the mounting itself for the CubeSats doesn't involve the CubeSat. The CubeSats just sit there, and then they're squished together by foam. So basically the only requirement that we'll have for the other people is just the dimensions, 10 by 10 by 10, and they can put whatever they want. Another thing is further down the track, say we want, you know, different avionics, maybe, I don't know, we can upgrade that very, very easily by just swapping out the removable boards. And furthermore, if we want to add anything else in the avionics bay, there's those threaded rods, which are obviously infinitely customizable. So yeah,
and we have developed a standard footprint for our PCBs to slot into the racks within the avionics bay. And there's the intention is that we have the couple main boards there, which is sort of like the fundamental boards, especially the power management board, which has the power supply and all those good features, and then the altimeter. And then there's a CAN bus on the altimeter, which can, you know, you can basically allows you to network between any other modules you might want to add. So I got a few ideas. I want to try out a few different radios, configurations, and antenna positionings within the avionics bay to see which gives the best. And there's an EMI testing facility in Perth here, which would be good to take a couple of different configurations down to test out the emissions of the radios when it's positioned in different ways. And then the other thing is, so we can try different modules for controlling the air brakes as well through the CAN bus, and we can try offloading the having like a dedicated module for the air brakes and completely offloading the main altimeter from the bulk of the workload, and that would allow us to potentially put an arbitrarily powerful microcontroller in there to do everything really fast, which would be good. I think NXP have like recently announced like a 1 gigahertz capable microcontroller or something, so maybe something like that would be pretty fun to try. Yeah.
Well, look, unless we're out of time, so you guys can go to bed now, okay? Or you can stay up all night. You're probably high on coffee already, so I know I would be if I had
I've been sipping. That's for
yeah.
sure.
All right. Well, look, you be careful then, and we'll hope to see you next year, okay?
Yeah.
Bye-bye.
Have a good one.
Bye.